Just to summarize what we're discussing yesterday, is the following. We talked about various knot polynomials and also a little bit about knot homologies, and those include simple examples. For example, we talked about John's polynomial. That's the simplest of all. We also talked about, so this is what we usually denote as P SL2, and it's associated to a two-dimensional representation of SL2, and it's polynomial in only one variable Q, so I'll write it in red. And conventionally in the literature sometimes the John's polynomials are denoted as J, so J of Q would be the appropriate notation. Okay, so then we also talked a little bit about Humphrey polynomial, which is a generalization. And here I'll draw for you a big diagram which summarizes relation between these different objects. So Humphrey polynomial is a polynomial in two variables. And again, since I'm trying to emphasize variables, I'll write them in red. So here we have two variables, the same quantum fellow Q, and also new variable A appears. And relation between these two is that if you want to obtain Jones from Humphrey, you are supposed to specialize to A equals Q squared, which corresponds to specialization to SL2 from a more general object. Now, these guys have further refinements, and this diagram will grow. In particular, each of these polynomials has categorification, and categorification is a homology theory which comes with an extra grading. So in this case it will be doubly graded, in this case it will be triply graded, and here we have Hovanov homology categorifying the Jones polynomial. H SL2 V2, same notation, and it's doubly graded Vij. And at the level of Poincare polynomial, if you wish, I'll write Poincare polynomial by this curly P to distinguish it from polynomial invariants that we're trying to categorify. So here you would gain one extra variable, which I'll call T, as we usually introduce in Poincare polynomial. So if you want to encode information about the ranks of these homology groups, you would be interested in this object, and you can treat it as a polynomial as well. But of course, it will have only positive coefficients and other interesting properties which reflect the homological origin of this Poincare polynomial. And likewise, a Humphrey polynomial has its own categorification, which is usually called Humphrey homology. And this is a triply graded theory. It has three gradings, I, J, and K. Or if you want to encode information about the ranks of these groups, you would do more or less the same. Take Poincare polynomial, and it will depend on A, Q, and T. So this is the most advanced form of life, if you wish. It has as many variables as you can hope for. And you can see that in this diagram, the number of variables progressively increases as you go from the simplest object, the Jones polynomial, to more advanced objects which involve either variable A or variable T, and relation between them is fairly clear. So if you want to go from here to here, you're supposed to set T equals -1 or take Euler characteristic. Likewise, this specialization is also achieved by setting T to -1. And these vertical arrows basically specialize variable A. As you can see, the top row contains variable A. The bottom row has no variable A involved. So therefore, this arrow as well could be viewed as specialization to A equals Q squared. So this is a summary of what we discussed yesterday. Some of these items we discussed in more detail. Some of them we discussed in less detail. But this is roughly what it looks in our yesterday discussion. So just as an example, let me give you our favorite trefoil knot. So when K is this knot here, then some of these objects look as follows. The most sophisticated guy that depends on 3 variables has the following form. It has, all of them have 3 terms, and it's very simple exercise to do the specialization. So this is A square Q square Q minus 2 plus A square Q square T square plus A to the 4 T cubed. Now this is object which we saw before. We saw it in the as a result of recursion relation. So Z1 from recursion relation that we got from algebraic curve was in fact exactly this polynomial with 3 terms, and it had exactly these 3 variables A, Q, and T. So it was the most sophisticated object from your homework. So there were 2 homeworks, one advanced, which I marked with a star, and one less advanced, which didn't have all the variables in there. There was only Q or something like that. Now, if you want to do specializations, then that's very easy. For example, if you set T minus 1, you get the Homfly polynomial, which indeed you can easily compute for this simple knot. Now, it's going to depend only on 2 variables, A and Q, and obviously has the form I just said T equals minus 1, so I get A square Q minus 2 plus A square Q square minus A to the 4. So then, if I want to specialize further, it's very easy to obtain this version or the Jones polynomial, which in this case would obviously be Q squared plus Q to the 6 minus Q to the 8. And this in turn is obtained as a specialization of this Chobanov homology. I'll just write it as KH, which depends on Q and T, and has the form Q square T to the 0 plus Q to the 6 T square minus, plus Q to the 8th T cubed. So in this case, it is indeed true that you can obtain Chobanov homology from this triply graded Homfly homology by simply specializing the grading, or in terms of variables, simply setting A equals Q squared. But this is not true in general. So this just happens to be so nice and simple in this particular example, because it's a very simple knot. But in general, I put this specialization in quotes because it has to be replaced by suitable operation in homological algebra, and in fact it involves some interesting differentials. So this is illustration of how this picture looks, and you saw earlier yesterday that this and this we can easily compute just on the back of the envelope on half a page on margins. These objects are very hard to compute from their definitions. They are well defined mathematically, but they're very hard to compute. However, the whole premise of this mini course is to show you alternative way which relates this objects to algebraic curves, and that's in some sense gives another way, another perspective on this very powerful invariance. Okay? In fact, when we worked with our algebraic curves and recursion relations, we not only had Z1, but we also had Zn. And this was a special case where n is equal to 1, of course. But we had all of them. So solving recursion relation immediately gave us all of the Zn's, so for all values of n. And these have their interpretation or their meaning in knot theory as well, because the entire diagram painted here can be easily decorated with additional piece of information. Say, the Homfly homology or Homfly polynomial, for example, has whole new dimension, or there is entire new variable, if you wish, that you can play with, namely a choice of representation. So let me pick some other chalk. There is so-called colored version of Homfly polynomial, just called colored Homfly polynomial, and it's labeled by Young tableau. And we already tacitly introduced this notation before. Likewise, Homfly homology can be labeled by any Young tableau, two-dimensional Young diagram, called colored version of this homological knot invariant. At the level of these polynomials in the bottom row, they have to do with changing representations. Remember, we discussed that there are quantum group invariants of knots and more generally three manifolds for any choice of Lie algebra and representation. So there was this more general R matrix technique which allows to compute or define such invariants. And for instance, if you pick this partition, two-dimensional Young tableau, to be just single row, say with n boxes, that's a very special case, of course, from a general perspective, but general enough for us because it gives another variable n and allows us to play with it. And then the only thing I have to change here is just replace this by n-dimensional representation here and here. So just like there exist definitions, I'm not going to give you these definitions for Homfly polynomials and homologies. There are other analogs here in the bottom row which involve high dimensional representations, and I already showed you how they rise in R matrix context. And if we have some time left, I'll be happy to give you definition, for example, for this object. So that's very simple. Just like John's polynomial can be defined by Skine relations, in a similar way, its colored version, so I should also write J sub n here, because now it depends on n, can be defined by very similar combinatorial rules. So there is a combinatorial definition which allows you to change crossing in a diagram of a knot and say how this invariant behaves under that. Okay, now that's enough. This is kind of roadmap or objects which exist in the world of quantum group invariants of knots. And now I promise to come back to another type of invariant. So now we're completely changing our gears. This is big picture or summary from last time. But now we're going to do something else and also talk about polynomials associated to knots and three manifolds, but in a very different way. It will be connected to this subject, but again, connection is exciting part in itself, and this is something new, something that's definitely worth investigating. But now we'll start from different branch of mathematical development that led to this. So this has to do with various moduli spaces, and the way it usually comes about is in the following way. This will come from a subject called gauge theory, and for most of it, at least in mathematical definition, this term gauge theory essentially means studying partial differential equations. PDEs on various manifolds, typically within low dimensional topology. So and in particular also PDEs involving gauge connection on some vector bundle or G bundle. And so on. So this is essentially a translation of what gauge theory usually means. It means that you want to write some PDE on 3-manifold, like in our case, or 4-manifold, as in lectures that Marcus Marini gave you, and study their solutions, which is usually a very interesting and delicate problem because it involves a lot of analysis. So, and we'll talk about specific version of it. In fact, we'll talk about Chern-Simons theory. And actually, you have seen already some bits and pieces of Chern-Simons theory in our earlier lectures, even though I didn't use these words. But we, in fact, introduced some of the ingredients which were secretly within Chern-Simons theory, and also in some other lectures as well. And Chern-Simons theory, if I have to summarize what it is about, again, just to give you a slogan of what it is basically the study of flat connections. In particular, in this theory, you do something with so-called moduli spaces of flat connections. And in particular, you can see that this is a special case of this PDE problem because what you're instructed to do is you're instructed to study some G bundle over manifold that you wish to study. For example, if you have some 3-manifold, I'll call it M, then you're supposed to study this G bundle over M and study solutions to the following equation, which is basically the flatness for the connection A dA plus A by J is equal to 0. So this form is, of course, the curvature 2 form for A, and usually is abbreviated like this. For this PDE, you're then defining moduli space, often written as curly M. So I'll write it as M flat to emphasize that we're interested in flat connections. It depends obviously on choice of the structure group G. It also depends on space on which you're studying this. In this case, say M3, and we'll define it to be, so this is definition, space of all such solutions, namely space of all such A's which satisfy this equation, and also modular conjugation by G, because we in gauge theory one does not distinguish solutions which are related by conjugation or so-called gauge equivalence. So this is a particular example of moduli space. So we have our basic ingredient here, which is our PDE. We study all solutions to this PDE, and now we'll start treating this as a space. So it often comes with a metric, which is not obvious, and also sometimes, actually in good situations rather often, comes with additional structure. And this structure is very important and not accidental, and our focus will be to study the so-called moduli spaces. These are spaces of solutions. So this is, in particular case, space of solutions or flat connections called moduli space of solutions, because this moduli, by definition, well, they're essentially parameters. This is synonymous to the word parameters. So therefore, the space is space of parameters. Parameters which parameterize solutions to this equation. Okay. Is this clear, or any questions? So therefore, this is how this story goes. It also feeds in a slightly more general perspective, which I should probably mention here, that there are, suppose, for example, we want to study some topological quantum field theory in the context of low-dimensional topology, very much like what you've heard from Marcus Mourinho. Or Seiberg-Witten theory, Donaldson-Witten theory, or something else. So all of these theories are called TQFTs, and they can be defined using axioms of Atiyah and Siegel. How do you spell it? Atiyah. Something like this. I always get confused. So these are axioms for what you should associate to different objects in your TQFT. Here we're interested in Chern-Simons theory, which is TQFT on 3 manifolds. So sometimes you would say 3-dimensional TQFT. So this 3 is the same 3 as we have here, because it deals with 3 manifolds. And according to Atiyah-Siegel axioms, it's basically a set of rules. What it is a set of rules what you're supposed to associate to various building blocks of your manifolds. In this case, 3 manifolds. So we can look, for instance, at closed 3 manifold. I don't know how to draw it because it's 3-dimensional. So well, I'll just write M3, okay? And to this, you're supposed to associate some sort of number, which is called partition function, and usually denoted Z of M3. So this is the same Z as or called the same by the same letter as what we saw earlier. In solving a recursion relation, and that's not an accident. Now, but if you want to build general 3 manifolds, you're allowed to build them from basic pieces by cutting and gluing, very much like what you saw in Renat Kashai's lectures. So in particular, you can also chop 3 manifolds along Riemann surfaces. So if you have a 2-manifold, which is a slice or cross-section of this 3-manifold, say Riemann surface sigma, which is boundary of M3 in our context, then to this, so I'll make a table, you're supposed to associate a vector space which is labeled by this Riemann surface, and in a physical definition of this TQFT arises as a Hilbert space. In fact, examples of this in a more complicated context you saw again in Mourinho's lectures. And then if you have a 3-manifold M3 which really has the sigma as a boundary, so if you picture, and we'll focus on this in more detail now, looks something like this. If this is Riemann surface sigma bounded by a 3-manifold M3, then this TQFT, or more general TQFT, is supposed to associate a particular vector. I'll just call it Z of M3, thinking of Z as a functor, which does this job, which takes us from left column to right column, seating inside this Hilbert space H sigma. And then this is kind of beginning of the axioms of Atiyah and Siegel, and the rest tells you how to glue things together. For instance, if you have a second manifold here, some other M3 prime, which has the same boundary, you can form a closed manifold, therefore landing yourself in the first row. And at the level of TQFT axioms, what it's supposed to give you is inner product between these two vectors in the Hilbert space. So this is a set of rules. If each half gives you a vector, then gluing two pieces together would correspond to taking inner product of these vectors and so on and so forth. So this is a very nice set of rules, and it's a nice summary of algebraic structure of any topological quantum field theory, be it Seiberg-Witten theory, Donaldson-Witten theory, or in our case, Chern-Simons theory. It's always a good question to ask, what are these axioms? What does it associate to 3-manifold, 2-manifold, and then you can actually continue down, ask what does it associate to 1-manifold or even a point. And that's always a good question. So it leads to very interesting, rich algebraic structure. Now, in this table, what I want to emphasize is that the first column is just ingredient in our topology, is part of the manifold that we wish to study. The last ingredient, at least in our story, will actually correspond to quantum object. So there is a functor which I call Z that takes us from topology to something quantum, and you already see that this is indeed very similar to our discussion of quantization, which fits nicely with this T-Siegel axioms. But luckily, this functor Z factors through something else. So in many cases, in most of the familiar TQFTs, in Donaldson-Witten theory that you discussed with Marcos, in Chern-Simons theory that we're discussing now, there is always intermediate stage. And luckily, it goes through something classical. In fact, through classical geometry. There is always a nice geometric object involved at intermediate stage in this dictionary before you land in a quantum world. For instance, this number is typically not just a random number. It can be nicely expressed geometrically as early characteristic of some moduli space. So first you associate to your 3-manifold, M3, some moduli space. I'll just schematically write M of M3. And then to get a number, you evaluate some numerical invariant of this space of solutions, like a space of flat connections. Likewise, if you have manifolds of all dimensions lower than dimension of your TQFT, there is always a way to associate moduli spaces to each ingredient. So there is M of sigma, there is moduli space of this fellow which has a boundary, and so on and so forth. And in all of these cases, the number that you get, the vector space, or more generally, even the category, is not just a random, complicated category. It's typically realized geometrically. So what's nice about TQFTs is that in almost all familiar cases, these objects, which are very algebraic, are realized in a nice geometric way. So that's why there is a beautiful connection often between gauge theory and geometric representation theory, because geometry is involved, and also there are some groups around, like structure groups. So this is the key reason why often there is a nice interplay with geometry and representation theory. Say, number could be viewed as basic numerical invariant of a manifold, such as early characteristic. The vector space could simply be cohomology. So in many TQFTs, this is what happens. You study space of solutions to some PDEs. You get geometric moduli space. I'll just call it M of sigma. And then you get vector space by simply taking cohomology. So this factor Z factors through this middle column, which is very nice and geometric. So the same thing happens in Chern-Simons theory, except that this second step is also non-trivial, is also interesting. It's not just taking cohomology of this moduli space, rather it has to do with quantization. So and that's our goal, to discuss this in a little bit more detail. Any questions about this so far? Is this kind of point or general picture clear? Okay. So, in the context of Chern-Simons theory, to which we come now, again, it's good to keep this big picture in mind. But in Chern-Simons theory, we're studying solutions to this flatness equation. So, to be very concrete, this moduli space for us is, in our case, is moduli space of flat connections with a structure group G and 3-manifold M. Likewise, this this moduli space here is moduli space of flat G connections on a Riemann surface sigma, and so on and so forth. So in each case, it's the same PDE, which essentially determines the kind of TQ of T that you want to study.
Always you consider on the trivial bundle.
For now, let's consider trivial bundle, but it doesn't have to be. So sometimes, especially if you're allowing, it depends on what you want to do. For now, let's just consider trivial bundle. Well, it will be flat, but not entirely trivial. So let's. Connection doesn't have to vanish, for instance, so it may have monodromies, for instance. So let's discuss that. So if you have, right, so what is this bundle, and what does such solution, what is it characterized by? So it is characterized, any flat connection on any manifold is characterized by its holonomy. So you always have to study homomorphism, a map, I'll call it rho, from fundamental group of whatever space you want to study, say Riemann surface, which we'll do in a second, or a 3-manifold, into the group G. Okay, and we're also interested in such spaces modular, such maps modular conjugation. So what this means is that if you have, so let me be a little bit more precise. For instance, in order to understand this vector space, the second row in this table, I have to look at the Riemann surface. So let's do that first, because that's much easier, and this is something very concrete, and then we'll move on to understanding flat connections on 3-manifolds. So here you have, say, Riemann surface. So our manifold is sigma, looks roughly as follows. This is typical picture of a Riemann surface. Let's say it has genus G. And then flat connection on such Riemann surface is characterized by its holonomies around all possible cycles. And in this case, as we know, there are 2G non-trivial cycles. There are A cycles and B cycles. One cycle's here. And I'll choose a basis of B cycles like this. So every flat connection will be characterized by holonomy of A, holonomy of our gauge field A around the cycles. I'll call them gamma, so gamma can stand for any A or B cycle here or any combination thereof. So in this case, there are H1 of Riemann surface is of dimension 2G. So there are 2G such different choices, and the curvature of the bundle is 0, so in that sense it's trivial, but holonomy of the gauge field is non-zero, so in that sense it is non-trivial. So it's a non-trivial flat bundle. And we're interested in studying parametrizing all possible solutions to this equation. In other words, we're interested in parametrizing all possible maps from fundamental group into our group G. Is this clear? So that would be, by definition, this is the definition of this space M. So let's understand that. This is actually not such a complicated problem. It's very easy to describe the space. And for most of the discussion, let me assume for a second that genus is greater or equal than 1. Because in low genus there are some special phenomena that often happen, and I don't want to be bothered with those. So how do we solve this problem, or how do we construct the moduli space? Well, we know that each of these holonomies is represented by is basically an element in G. So by definition, this holonomy is integral of one form A around this one cycle. So it's one form as a perfect object to be integrated over one cycle, and that gives you an element in G as a result of this integration, path-ordered integration. So therefore, you have a bunch of such holonomies. I'll call them AI and BI for where I runs from 1 up to G for corresponding matrices or G-valued elements which represent these holonomies. Okay. Then if you wish to study this map from fundamental group into G, or characterize flat connection, this homomorphism, all you have to do, you have to study the relation in the fundamental group of a Riemann surface and write it in terms of these holonomies. And we know that fundamental group of a Riemann surface has very simple form. It's say A1, B1. Well, it's generated by this one cycles A and B with the relation A1, B1, A1 inverse, B1 inverse, and so on up to AG, BG, AG inverse, BG inverse equal to 1. Okay. So this is a relation in fundamental group of a Riemann surface on 2G generators. Now, if we wish to study this homomorphism, we simply replace each generator by G-valued element, which represents the corresponding holonomy. That's it. So for instance, if our group is SU2 or SLN, we just replace A's and B's by corresponding n by n matrices. That's it. So is this clear? So each of this takes values in G. Now, and in a way it gives a parametrization or characterization of the moduli space of solutions, because moduli various details which are interesting and depend on details of what you want to study, stability conditions and so on. This is essentially characterization of this homomorphism from fundamental group in a G. It's given by G-valued variables with G-valued relation imposed on them, because this now is a relation in a group. I mean, this identity, for example, is meant to be understood as identity in G. So therefore, what we can easily do is, for instance, count the dimension of the space. So what we're ready to do is to write dimension of moduli space of, say, flat connections G connections on a Riemann surface of genus G. And let's count this dimension. It's basically the number of variables or parameters you can tune, modular relations that you impose. So it will be variables minus relations. So variables are various elements, parameters contains in A's and B's. So we have 2G times dimension of G parameters, okay? Coming just from elements of A and B. Again, if you think of A's and B's as matrices, that's what we have. Then we have to impose this relation because these matrices satisfy the matrix equation where they're supposed to be equal to identity. So there is a dim G relations imposed. And we actually also have to subtract another copy of dimension of the group if you are interested in solutions to this up to conjugation. Conjugation means that A's and B's are conjugated in the same way, all of them, by the same matrix, which comes from gauge equivalence or our desire to impose that as a definition of the space of solutions. So as a result, you get twice G minus 1 dim G dimensional space of solutions or parameters. So we characterized parameters that for each value of these parameters, we have a flat connection on the Riemann surface. So it's very concrete, very explicit, and for 3 manifolds, it's going to be just as simple and explicit. So in a moment, we're going to do it for 3 manifolds. I just wanted to walk you through 2-dimensional case because this is something very, very concrete. In fact, it's a perfect place to stop for a break, which we'll do in a second. But let me make a couple of remarks about this result or calculation. First of all, you see that it was indeed convenient for me to pick genus greater or equal than 1. Otherwise, I would run to some negative numbers. In fact, even for genus equal to 1, as we'll see after the break, we have to do a slight modification. This formula is not quite right. So it's good to assume that genus is fairly big, so you don't get negative dimensions. But more importantly, this is not the remark I want to make. A remark I want to make is that it came out to be always even number. And that's nice. So in fact, remarks is that, first of all, this M flat G sigma is always symplectic. And remember when I talked to you about symplectic manifolds in the very beginning as a starting point of quantization, it was actually not so easy to construct non-trivial examples of symplectic manifolds which have interesting topology and come for a good reason. And understanding these examples was rather non-trivial. So this gives you already a very nice family, whole class of symplectic manifolds coming from gauge theory, and they're labeled by gauge group and a manifold. So that's pretty cool. You have lots of examples of symplectic manifolds which could be used as a starting point for quantization. So all of this, it's a theorem. Well, I put it as a remark, but it's a theorem that this is actually symplectic manifold. Symplectic for all choices of G and sigma and Riemann surface. Now, another remark, which is kind of building up on the first point, is that you get even more. We'll talk about symplectic structure here in just a second. Well, maybe, I should probably write it in a schematic form, but after the break, I'll explain it a little bit more concretely. So there is a canonical symplectic form you can construct, which is due to IT in Both, obtained by taking the trace of variation of one form on a Riemann surface and also now on the moduli space. So this del is a differential on the moduli space. So it is a 2-form on sigma as well as a 2-form on our space of flat solutions. And you can construct something nice out of it by integrating over sigma. Then you just get a 2-form on the moduli space. So that's that's a symplectic form. Again, it may look too abstract if you haven't seen it before. I'll explain it much more concretely after the break. But another related point, so another theorem, is that you get even more structure. So here, remember that each symplectic manifold has to have even dimension, and that's what we have here. And that's attention I'm drawing to this factor of 2. But you get even more if you look at M flat for the group which is complexification of G. So then you get something more. You get actually hyperkähler examples of hyperkähler manifolds. And the same expression for this symplectic form automatically gives you actually holomorphic symplectic structure. And there is a little bit more you need to get not just holomorphic symplectic, but rather hyperkähler geometry. So since we already discussed complexification before, it will be very natural to work with these examples, which have twice the dimension of these fellows. And this will be very, very nice phase spaces for quantization. So in fact, what I'm trying to do now, I'm trying to come to the examples which we already discussed. So all of these we actually did secretly discuss before. I never used any of these words, gauge theory or TQFT or anything like that. But we're coming back to same quantization problems we saw in a completely unrelated context. So let's take a break, and after that I'll spell out the details of these telegraphic remarks, and it will be actually very simple to generalize this for 3 manifolds. So let's do 15-minute break. This kind of covers general case and mostly when genus is greater than 1. So let's aim to kill 2 birds with the same stone. First, move on toward the exceptional case where genus is equal to 1. This is not entirely covered by this statement, as you'll see in a moment, because dimension is actually not 0, as this formula seems to suggest. And also, it will be a very simple case. So you can see that everything can be done with hands-on approach. So I'm going to focus on special case or example, but this is exactly the case that we're mostly interested in. Example where genus is 1, so sigma is simply a 2-dimensional torus. So there is only one A cycle and one B cycle. And along each of the cycles, we have corresponding holonomies. We have this elements. So here we have, say, A. Here we have G-valued element B. And now this relation here simply says that A and B commute. So in fact, now having 2 matrices G-valued objects which commute, we can simultaneously conjugate them to, say, diagonal form. So in particular, we can represent A, which is holonomy of our gauge field over A cycle, and B, which is holonomy of gauge field over B cycle, to say diagonal form, or form which looks something like this. We have something on a diagonal and zeros in the lower diagonal part and something over here. So of course, it's natural, and in most, for generic values of such holonomies, it's actually possible to conjugate this to the form where you also have zeros over here, and you only have diagonal elements. I'll call them x. So this x is a vector. Number of x's is equal to the rank of the group, G. So then you can bring B eigenvalues to the same form. On a diagonal, you'll have some bunch of numbers from 1 up to rank of the group, rank of G, such numbers on a diagonal, and say zeros everywhere else. Sometimes it's not quite possible. For instance, if you have values of x or y which are coincident, then you may have non-trivial Jordan form. But I'm not going to be worried with these cases. Anyway, very concretely, again, you have two matrices. Generically, since we're interested only up to conjugation, we can use this conjugation symmetry to put them to the diagonal form. And therefore, what we really conclude is that this moduli space, M flat G for Riemann surface of genus 1, which is just a torus, is made out of two copies of the maximal torus of the group G. So I'll call this maximal torus by T. So this boldface T sitting in G is maximal torus in the group, not the one we're working with, obviously. So we have two fellows, T times T. And we used up all of the conjugation to put these elements A and B, which are G-valued elements, to the same diagonal form, well, to their own diagonal form, but there is a little bit left over. We're allowed to make permutation of these eigenvalues, xi and yi, so we have to divide by the Weil symmetry, which is a finite group. For example, if you're working with GLN, it will be symmetric group on n elements, and maximal torus will be n-dimensional torus in that case. So this is a particular illustration of how this moduli space is described very concretely. It's a nice space. In fact, not quite. You see it's an orbifold because this group has some fixed points, and but at least it's a nice quotient space. And it has even dimensions simply because no matter what this maximal torus is, you have two copies of it. You have a natural symplectic form. In fact, symplectic form in these notations is exactly the form we saw before. It's dy over y wedge dx over x. Okay. Now I'm going to specialize actually even further. So let's specialize even further, and given that we gain a lot more by considering complex groups, I'll talk about this hyperkähler case, which is given by complexification of G. So I'll put a subscript C here. So we'll consider complexified group GC. Here we have complex torus just by analytically continuing all the elements in the maximal torus to their complex values. So here we have two copies of complex torus then, and you see that real dimension of the space is obviously multiple of 4, which is necessary requirement for hyperkähler manifold. And this then becomes y is complex, x is complex, and this is holomorphic symplectic form. So in fact, the simplest non-trivial case is when rank of G is equal to 1. So I don't want to be worried with these indices and matrix elements. Let's just consider the first non-trivial case. So then it's natural to choose this complex group to be SL2C, which is complexification of, say, SU2. Okay. So in that case, these elements A and B can be brought to the form x inverse, 0 and something, and B likewise can be brought to the form y inverse, 0 and something, and they parameterize our favorite space, which I'm going to write one more time. So this M flat in this case is just C star cross C star mod Z2. So Z2 is a Weil group of SL2, obviously. The Z2 acts by sending x to 1 over x and y to 1 over I simultaneously. It's the leftover conjugation symmetry that we have.
So we proved some exceptional summaries So when A and B have the same chosen form, non-trivial chosen form, so we throw it.
Well, you have to be a little bit.
Point in our space.
Yeah. Well, this point happens where x is equal to when x and x inverse coincide. So the equation, so something interesting happens when x equals x inverse, so when x squared is equal to 1. So at plus minus 1 points this occurs. So these are the points where we have to be a little bit careful. And actually notice that...
So this is not the whole space, but just a plus.
Exactly. So this is, right, so this is generic point of the space. It describes smooth component, but there could be either some things we have to add or some things we have to exclude. And notice that these points where I have to worry about the star, so if x and x inverse are distinct, then I can equally well just write 0 here, because then I can conjugate fully in the maximal torus. When they coincide, something interesting happens. I have to worry about the star, because it may be in the Jordan form in a sense that this is 1, 1, and then some number here, which I can rescale, but I can get rid of. But this point is exactly the one where the symmetry acts non-freely. So these are precisely the orbifold or singular points in this moduli space. So what this moduli space looks like, again, if I had I'll try to draw a cartoon. So it's, if we were talking about real version, it would be S1 cross S1 if I was talking about SU2. So I decided to go to complex group, but if it was SU2, it would be S1 cross S1 mod Z2. So it would be so-called pillowcase, which is torus divided by Z2, divided meaning that there are 4 bed points. So this is S1 cross S1 picture, divided by Z2, and it has 4 fixed points under this action. So once you do the division, you can see that this is actually, the result is a sphere. Topologically, it's a sphere, but very funny sphere, which has 4 corners. So these fixed points become corners, and this is called pillowcase. This is what you put on your pillow. So. It's like a sphere, but it has 4 singular points which originate from this orbifold. And again, it's even dimensional space. Notice that this is very much like our baby example for quantization, like a usual sphere. It's good for quantization because it has symplectic structure and so on, except for the singularities, which actually make life interesting if we go further, but we're not going to do it today. So. Yeah, so this is kind of in quotes. This is impressionistic picture of this moduli space. If it was real slice of this picture. In complex world, it's of course this quotient, and not surprisingly, we already saw this C star cross C star before, where each copy of C star is parameterized by x and y, which are eigenvalues of this matrices here. Okay, and in fact, this symplectic form, for which I omitted all the indices, is exactly the symplectic structure that you get from this general formula specializing to the rank 1 case. So that gives a rather explicit and concrete description of what this space is in the genus 1 case. And that will be good enough for our applications. And luckily, this space is almost flat, almost boring. I mean, it consists of maximal torus, modulus, and quotient. So any questions, further questions about this part? So because the space comes with a symplectic structure, which in fact does follow from Chern-Simons theory, and maybe I should just give a quick quick argument how and why that happens, because this is rather crucial element. So our equation FA, which is dA plus A wedge A equals 0, follows from variational principle. So it's an equation where you have so-called Chern-Simons functional S of A, and S of A has this famous form where it's 1 over 4 pi integral over 3 manifold of trace ADA plus 2/3 A wedge A. So this functional is called Chern-Simons functional. And that's the reason why this topological theory that we're developing on 3 manifolds is called Chern-Simons theory, because it's based on PDEs that follow from this functional. But in order to get, so it's nice that we got this symplectic form. And this expression, either in general form on that blackboard or this concrete one over here, exists. That's nice. That's a nice symplectic form. It's easy to check that it satisfies all the required properties. But of course, the reason I'm telling you this is because not only we want to have a fact that this is a symplectic manifold, we want to use it as a starting point for quantization. We want to start thinking about this space as a phase space. So we want to treat it as a starting point for doing something with symplectic geometry that we got. So now we have a lot of luxury. If you have a symplectic space, do something with it. Either study Gromov-Witten invariance, or Fukaya category, or Lagrangian submanifolds, or quantize it. So if you got symplectic space, it's good to use it. So it is a very simple symplectic space, and in a moment we'll see interesting Lagrangian submanifolds. So we should use it. So we should use it as a phase space. But my point is that it's not really a choice. This is what you have to do according to Chern-Simons theory. I'm not going to explain all the physics that goes into it, but I'll just point out the following. The way you obtain symplectic form on your classical phase space is you write the action in the form PDQ, usually. So and there could be various other terms related to the potential and so on and so forth. So to write it in this form, if you have, so this is typically what you write in Hamiltonian, because there is a momentum and coordinate. If you have Lagrangian, what you should look for is analogous term which involves time derivative. So typical momentum, after all, is a time derivative of coordinate, and what you usually look for is terms like variable q times time derivative of q. Okay? And in this case, you see that this d is exterior derivative, but if you treat your 3-manifold M3 as R cross Riemann surface sigma, and you parameterize this R by time, so T stands for time, then there is a term here which has the form trace A dt A, where I take component of this exterior derivative along the R direction. And then this will be a two-form on sigma. Okay? So therefore, even if you're not accept, I mean, this is a mathematical fact that these spaces have symplectic structure. So, but what I'm trying to explain is that it doesn't come as a luxury. It actually comes as a necessity. So if you're instructed to derive symplectic structure from Chern-Simons functional, this is exactly the one you would derive. And I'm sketching for you important steps. So it comes from this term, from this quadratic term over here, on a 3-manifold in the form R cross Riemann surface. So therefore, it's a good homework problem. And again, this is a key ingredient. To derive the symplectic form I just erased, or which was on that blackboard, from this functional. So in order to do this, you have to assume your manifold is in this form and try to write the kinetic term, this quadratic term, in a canonical form, where you have PDQ or AA dot type structure. So anyway, this is just quick remark that this symplectic structure is something that comes automatically and for a good reason. Now let's move on to three manifolds. In the case of three manifolds, we're supposed to study analogous problems. So we again have representations. All the flat connections are characterized by representation from fundamental group. Now in this case, from fundamental group of a three manifold into our group G, or if I decide to work with complex group, into GC, modular conjugation. Okay, that's again some nice moduli problem that involves solving PDEs and so on. But good news is that very much like for Riemann surface, fundamental group of a three manifold is usually presented to you in form of some generators and relations. So all you have to do is to write those generators and relations in terms of G or GC valued matrices, and that's it. Very much like we did for Riemann surface, you can just take generators relations, write them in terms of, say, SL2C matrices, and that will be your parametrization of this space. And something nice comes out of it. Moreover, again, let's be simple. Let's once and for all choose our group to be SL2C, the simplest non-abelian group, so we get something non-trivial. And also let's choose three manifolds M3 to be to have toral boundary. So this is a case similar to what I was drawing before, where you have a three manifold whose boundary is a torus. So this is M3, this is T2, and why is it relevant, or why is it interesting for us? It is interesting because if you want to study knots, and we saw lots of knot invariants, you can do the following. If you take knot in a three-dimensional space, R3, or equivalently three-sphere if you compactify at a point at infinity, so this is cartoon for a three-sphere, and if you're interested in studying a knot, like our trefoil knot in a three-sphere, what you can do, you can equivalently obtain all the same information about topology and geometry by doing the following. You can take a tubular neighborhood of this knot, which is a little solid torus that goes along with it. So it basically traverses the knot, and remove it from the three-sphere. So what this does for you is, the result of this construction is a three manifold M3 called knot complement, which takes away neighborhood of the knot K from the three-sphere. And the resulting manifold is going to be exactly of this type, namely it will have a toral boundary, because the boundary of this tubular neighborhood of a knot is a solid torus. Knot itself is a circle, then there is a tiny circle linking it, here I draw this in red, and those two together form a boundary torus. So therefore every information about every knot is encoded equivalently in this space here. Okay. So therefore, this is not really just a specialization which has no good motivation. It covers all the knots that we discussed before. It has direct application to knot theory. Okay, so now let's do the following. We wish to study a space of flat connections, which are again characterized by homomorphisms, fundamental group into complex group. But it's always a good question to ask, how does it relate to moduli space or representation space for this boundary torus? Because that we analyzed in detail. And if you have a flat connection on a 3-manifold, you can simply look at its restriction on a boundary torus. And what this gives you, it gives you an embedding of M flat of, again, GC on a 3-manifold inside the moduli space of flat connections on the boundary. Simply by looking at restriction, if you have some gauge field A here, you can look at A restricted to sigma, and if it satisfied flatness equations on a 3-manifold, surely it will be flat on the boundary torus, right? So therefore, every solution to equation on a bigger space obviously gives you a solution to PDE on a smaller space for very...
Why do you write that this is injection?
Well, I mean, whatever I'm going to write is not going to be going to be subtle precisely because of singular points. Let me just write that it's contained. Okay, contained.
There are several ways to continue the flat connection from sigma to whole manifold.
No. So yeah. So it's okay. So this is a theorem. I'm not going to present proof, which involves easy part and hard part. So easy part is to work with generic flat connection, and I would have to explain a lot more technology. For example, introduce definition of so-called reducible, irreducible flat connections and so on, because it now is going to be very delicate and sensitive to whether the structure group for that particular flat connection is all of our group or some smaller subgroup. If there is a non-trivial stabilizer, then you actually are right. So, but the statement in the end will be correct, but there will be a lot of technical little details that I would have to fill. So therefore, it's just easier for me to state it.
Without technical details, it's quite clear. I mean, if you forget about that, because it's just here we have all homomorphism, and here we have ones which are trivial on the part which is contactable in the bigger manifold.
Exactly.
So on the level of homomorphism from Poisson group, it's clear, and if you pass to the moduli space, it's much harder.
So maybe to convince you guys, let me consider an example which is essentially equivalent to proving this theorem in this easy case, which avoids all this reducible and delicate singular points. So let's, and it will illustrate all the key features. So let's consider a simple example where our knot is unknot. So we'll just walk through this picture. So K is unknot. This is what I was drawing earlier by this simple circle. It has no knottedness. It's not even trefoil. So let's understand what is the story there. Okay. We want to take this knot and excavate it from a 3-dimensional space. So I'm supposed to take a neighborhood of it, which is what I'm drawing by this very thick solid torus, removing it. So then, as a result, what I get is a complement, a 3-sphere minus a knot, but that's going to be also a solid torus. In fact, the boundary of this torus is exactly the boundary of everything outside of it. So this is also solid torus, or S1 cross a 2-dimensional disk. Okay. Now, on the so the boundary of M3 is clearly just the usual torus, simply because boundary of S1 cross a two-dimensional disk is S1 cross S1. Okay. And now you see what's going on. So fundamental group of a boundary torus here, pi1 of T2 is Z times Z. Okay. And fundamental group of M3 that we want to study, pi1 of M3 is just Z. Because one generator of this group is killed, is contractible in the knot complement. So in fact, what's going on is the following. So here in orange, so I'll draw several more cross sections. We see the following. This orange loop is contractible in the neighborhood of the knot K. And this is called meridian. So this orange guy is called meridian because it goes around the knot. This white loop over here, which essentially traverses the knot, and I can pick analogous cycle, say on some cycle which goes here on the boundary torus on a T2. This is called longitude. And it is non-contractible in the neighborhood of the knot itself. Because, yeah, it's fairly clear. The converse happens in the complement. So longitude is contractible in the knot complement, which is S3 minus K. And meridian becomes non-contractible. Meridian is non-contractible. So let me put it as a homework. So prove this statement. So homework assignment is show this. These two statements. It involves a little bit of visualization and working with the definition of taking the complement, but it's fairly straightforward. But it's of course important to do that. So as a result, you'll see that, well, in any case, it's clear that one of the generators of the fundamental group of the boundary torus, T2, is killed once we're trying to look at the fundamental group of the complement, S3 minus K. And as a result, you go from Z times Z to only Z. Now, it's very easy to study homomorphisms from Z times Z and Z into say SL2 as we did here. So in fact, I don't even have to erase too much on the blackboard. We already have all the relevant pictures. So in the case of T2, homomorphism from Z times Z into SL2C modular conjugation is given by two copies of maximal torus, so it's parametrized by X and Y. So that's that. On the other hand, if you're interested now in homomorphism of this group Z into SL2C, you have only one copy of maximal torus. So in fact, there is one relation which corresponds to the fact that now longitude is contractible here. And if longitude, for example, corresponds to holonomy around, say, B cycle, then at the level of fundamental group for M3, which is Z, you have one relation. You have no restriction on meridian, but you have a restriction that longitude should be trivial. So it's a group generated as before by A and B, but now we impose a relation that B is trivial. Okay? So therefore, as a result, your space of flat connections or homomorphisms from fundamental group of a 3-manifold into SL2C is just a single copy It's so I'm going to erase this to free up some space. It's a set of points x and y which belong in here, but with an additional relation that y is equal to 1. Okay. And this relation arises precisely because longitude becomes contractible now in a 3-manifold. So the idea is very simple, that if you go from Riemann surface to 3-manifold, you can look at the same generators, but now you have more relations. And that's why, in general, you have this containment that this space is embedded as a space here. In fact, exactly half of the cycles become contractible. If you think about this genus G Riemann surface example we discussed before, you can think of a 3-dimensional manifold which is a Handel body. So you take half of the cycles and make them contractible. This is analogous to the solid torus that we just discussed. And as a result, you'll see that this moduli space is in fact half-dimensional, even if we consider high genus Riemann surfaces or other groups other than rank 1 case, it will always be half-dimensional at generic points. So this is a very nice, beautiful Lagrangian submanifold. Sorry? Exactly. So it's passing through some of the singular points. So here, this space is singular at points where y and x are plus minus 1. So away from those points, for example, if I let x be arbitrary, a point where x is square root of 5 and y is equal to 1, that's a non-singular point. So only when they're both plus minus 1, that's a singularity. So, but indeed, it's important that it passes through singularity. So indeed, that's what makes the story interesting. That's why some of the hardcore applications, I mean, they have to do with singularities. That's true. Yeah. But generic points are away from the singularities. Okay, so this is in fact an example of our algebraic curve. Because in the rank 1 case that we're discussing and in application to knots, you see that we recovered our phase space, which we use to quantize. It comes with a symplectic form. And that's a 2-dimensional space parameterized by x and y. We just recovered one condition, algebraic equation, of the form a of xy equals 0, where in this case a is just y minus 1. As an equation that describes flat connections which extend to 3-manifold, or in this case, not complement. So this is how algebraic curves start appear in this business. So in fact, now let me phrase a more general theorem, and we'll stop there. This is in fact now fills all the gaps that we had before, or connects all the elements that we saw earlier. So as before, let group to be SL2C, just so we work with the simplest non-abelian group. Let's focus on the case which has something to do with knots, because our applications did involve knots as well. So we take M3 to be 3-sphere minus k, not complement. And these are examples of manifolds which have toral boundary. Then the following theorem holds. And it's due to 5 authors. And to save time, I'm not going to write all the names on the blackboard. They are in this review I gave you archive number for yesterday. So the theorem, first part of the theorem says that, and it's very obvious, but I'll include it in here, even though it's a trivial statement, that in our notations, so this moduli space of flat SL2C connections on a boundary of M3 is just C star cross C star mod Z2 parameterized by holonomy eigenvalues x and y. So x and y are the C star valued variables, modulo this minor detail that you have to remember about Z2 involution. And interesting part of the theorem says that M flat GC, now not on a boundary, but all of M3. And again, there are some obvious details which have to do with singularities and how exactly we define the space, but again, I'm going to skip this because it's not important for any of the applications. The space is actually a space of flat connections on the boundary torus. So again, picture is that you have 3-manifold bounded by T2. This is our M3, and generic flat connection on a torus can no longer be extended to all of M3 because there are additional relations. That's exactly what we encountered here in this basic torus example. But some of them can, and exactly half-dimensional space of such solutions can be extended. And those which can, in this case, are exactly described by algebraic curve with some polynomial relation where this object is a not invariant. In fact, it's a polynomial invariant, and for lack of better name, it was just called a polynomial. But it has a very different nature than this polynomial invariance we discussed before. So I want to finish by giving you properties, summarizing some of the properties of this A polynomial. You can view this as a defining property if you wish. So this can be, the statement is that this moduli space is algebraic, is described by algebraic curve, and this is a definition of A, if you wish. In fact, it's easy to see that it's algebraic from the GIT type quotient construction by very much like what we did in the case of Riemann surface. You write GC valued elements, modular conjugation, oppose all the relations that come from relations on the fundamental group generators, and that's how you get this guy. Anyway, some of the properties. So, first of all, for any knot complement, fundamental group is very interesting, and that's what contains all the information about these flat connections, solutions to PDEs. But first, homology is very simple. It's always Z, and sometimes possibly there is a little bit of torsion, but it always has rank 1. So first Betti number of this knot complement is always 1. So as a result, so for any knot complement, so as a result, there are always flat connections or homomorphisms from fundamental group of M3 which factor through something abelian. And what this means is that this invariant called A polynomial always contains the piece y minus 1 times possibly something else. And this y minus 1 is exactly the guy we discovered here. So it may have several factors. So it may describe a reducible curve. And one component is always this line that we just saw very explicitly in concrete examples. So claim is that this is a general property. That always happens.
Why do we have this factor? Y minus 1?
Well, because we are interested in Holmes from pi 1, but then I claim that they factor through abelianization of pi 1. well, at least there are some Holmes which factor, and these are easy to study. This is always Z, and then you study it further how this maps into SL2C, which we already did. So that's the claim. We just did that. Now, in the opposite direction, you can wonder if this is generic case, or conversely, you can ask how far is generic A from this factor. So in other words, how much is in this non-abelian representation? How often does it occur? And this will give some information how strong invariant of a knot this is. And the statement is that if your knot is hyperbolic, this is a technical term, but actually what it means is that its complement has constant curvature, constant negative curvature metric. And in fact, according to Thurston, most of the knots are hyperbolic. So in fact, this is a rather generic statement. So then if knot is hyperbolic, then theorem says that A of xy is strictly bigger than this y minus 1 factor. So there is always something in here. So it is actually rather interesting and powerful, and so on. So other properties of this knot invariant are the following, just to give you a couple. I'm not going to continue too far. In fact, this is about time to stop. But just to give you a flavor, and we already saw example in our completely different approach. We were quantizing algebraic curves, and I picked exactly this example as a starting point for quantization, because as you see, we have beautiful phase space, we have Lagrangian submanifold. This is what it is. And some of these properties you can actually check in the example that we used. For instance, this A polynomial is also reciprocal, meaning that A of xy is similar up to multiplication by any power of x and y to polynomial where x is replaced with x inverse and y is replaced with y inverse. And notice that this has to be true in order for it to sit in this quotient space, because that's how our Z2 symmetry acts. So if this property was not satisfied, it would make no sense to write this embedding that I insisted on, or view it as a Lagrangian submanifold. So it surely has to respect the symmetry of ambient space. And the symbol means up to multiplication by powers of x and y, and that's okay because only the zero locus of this polynomial is meaningful, according to the definition. And the last property that I'm going to give you, which is kind of curious, is that even though I'm emphasizing that such polynomials which come from moduli spaces, which describe algebraic geometry of moduli spaces, are very different from quantum invariants, here there is something mysterious too. It always happened to have integer coefficients. So this A polynomial a priori could have rational coefficients. That's not so hard to show. But it's actually well, I don't know any way to show that it has to have integer coefficients. Well, sorry, I'm not saying it well. For a polynomial, it's easy, but for analogous high-dimensional problems, it's mysterious. Anyway, here there are, so it has, let me write it, and I'll make a remark in just a second. Has integer coefficients, which is already quite nice property. It continues to hold in higher dimension. So in this case of one-dimensional curve, it's actually not so hard to see. It has generalization to high-dimensional moduli spaces. For example, if you increase the rank of the group, this analogous property will hold, and there it's completely non-obvious, and it's total mystery. So therefore, the fact that there is a baby explanation in rank 1 case doesn't actually help much. So this is kind of misleading. Moreover, it's not so much integrality of these coefficients. It has a lot of interesting number theory built in. So the reason I mentioned this last remark here is that if you look at various numerical invariants of this A polynomial, as a number theorist, you'll immediately recognize lots of cool things. You'll recognize cyclotomic polynomials, various number fields attached to this polynomial. So there is a lot of cool stuff. So it's not just integrality of coefficients, but even on top of it, there are very special integer numbers. So that's what I'm trying to say. So maybe I should say has special integer coefficients. And then this will be a meaningful, precise remark. Anyway, you saw examples of this polynomial before in our original approach. And I guess this gives you an idea where such algebraic curves come from. They come from, their zero locus typically describe some moduli space. And I hope I at least managed to motivate why quantization is useful. OK, so I'll stop here.